So the antiderivative. Not that hard to understand. Instead of going from the function to the derivative, we go from the derivative to the function. Not too bad, right? Okay, so let's say that I have f of x equals x cubed. What's the derivative, class?
3x squared.
3x squared. Oh, yeah. What if I have g of x equal to x cubed plus 10? What's the derivative?
3x
squared.
3x squared. Okay. If I have h of x equal to x cubed minus 22.
3x squared.
Derivative 3x squared. That's kind of interesting. All right. So, no big deal. I'm going to tell you that here's the derivative. We'll call it m prime of x. So I'm going to tell you the derivative. It's 3x squared. What is the original function?
X.
X cubed.
It could be x cubed.
X
That could be
cubed
X cubed? Okay.
Plus or minus, I think.
plus something.
Plus something.
It could just be x cubed.
It could be x cubed, in which case the something is nothing.
Oh.
Right? It goes plus 0.
Oh.
Right? But yeah, it could be plus 10, it could be minus 22, it could be plus 0, it could be anything. Well, it couldn't be anything. I mean, it couldn't be plus sine x. Because if it was plus sine x, then when you took the derivative of that, you would have 3x squared plus cosine x. Right? So it can't be a sine. What else could it not be? It would be a cosine. Yeah, it can't be a function of x. So what does that mean?
It has to be a constant.
It has to be a constant.
Oh.
It has to be an integer, yeah. Alright, so we
Plus or minus constant.
you could put plus or minus constant, but we're gonna be super lazy. We're just gonna say plus a constant, and then everyone knows that a constant can be negative. So we are filming, right?
Mm-hmm.
Alright, get that, guys? Good. So it could be, yeah, that's great. And this is called the constant of integration. You're like, why is it called constant of integration? Wait till next week. Oh, yeah, plus C. There was a math teacher, Mr. Siri, he used to work here, and then he went and taught somewhere else. And he talked about how in his Calculus 1 class in college, he forgot to put plus C on his answers for one of the quizzes. And it turned like a 95 into an 85 because he just forgot to do that. So then from then on, whenever he was taking his quizzes and tests, he would put at the top of the paper, put plus C as a reminder to himself to do that. Okay, so as long as we all remember, when we are doing the antiderivative process, so when we're going from here to here, doing the antiderivative, you have to put plus C at the end because you don't know if you're dealing with, what that actual function is going to be. Now, that's kind of the hard part. That's the part that everybody forgets. What we now need to do is just sort of think through what are the rules for antiderivatives. Okay? So, I kind of prepped you on this one to say that 3x squared would turn into x cubed. Okay? But what if it was something different? What if, for instance, we had f prime of x equals x to the fourth. What is the process to find the antiderivative of that?
Well,
Oh,
it'd be
we technically have.
Well, we know it would be, well,
x to the first, right? It'd be
it wouldn't be x to the first, it would, we know that it would be x to the fifth, because normally you have a pop down, power down situation, so you normally would pop down the 5 and then power down. So since this is a 4, we know that this has to be a 5, okay? The problem is that if we think about that, if you take the derivative of x to the
We
fifth,
should have a 5.
you would have 5x to the fourth. Times 0, I don't get it.
You just times the 5 by 0, it's gone.
Oh, exactly. No, what you, the way we're going to kind of think about this is we're doing pretty much everything the opposite, okay? So here, we powered down, so we decreased it by a number. When we're, for the derivative, when we're doing the antiderivative, we're increasing it by a number. When you were doing the derivative, you took that number and multiplied it by this. When you're doing the antiderivative, you take that number and you divide. So f of x would equal x to the fifth over 5. Let's check that together real quick. What's the derivative of x to the fifth over 5, class?
1.
So,
it'd be 5x to the fourth over 5.
5x to the fourth over 5. And then
Should cancel.
We're gonna cancel.
they cancel, and you end up with just x to the fourth. Let's do another one. What about f prime of x equals x to the third, I guess. The antiderivative would be x to the
To the fourth over.
x to the fourth
Over 4.
over 4. Let's verify that. Take the derivative here. Pop down the 4. Power down the 4. So if you pop that 4 down, it'd be 4 as a multiplier. 4x cubed over 4. Okay, seems to work, right? If you think about it, the derivative of x to the n was, think about the process. Process 1, pop down, so multiply, then multiply by the exponent, then decrease the exponent. Now, what we're doing, so if you have x to the n, the new process is, it's the complete opposite reversal of everything. It's do the last operation first, and the first operation last, and do every operation in the inverse method. Okay? So in other words, step number 1 was multiply by n. Step number 2 was subtract 1 from n, right? So now we're doing the reverse process. So we're going to add 1 to n, so x to the n plus 1, and then step 2, divide by that n plus 1 term. So x to the n plus 1 divided by n plus 1. But wait, don't forget plus c. You see what I said? It's the reverse order of operations and yeah, it's kind of, anyway, it's kind of, all right, Terminology. Symbols. We knew that this is the symbol for take the derivative of this function. Now I'm going to show you the notation for take the antiderivative. Okay? It's kind of a long S type thing. And then you write dx after the function. So you have this symbol right here, the antiderivative symbol. Then you have the function you're taking the antiderivative of. Then you have dx, which lets you know that the x is your variable of integration, or the variable that you're taking the antiderivative of. And then we would say equals x to the n plus 1 over n plus 1 plus c. Alrighty then. So, applying what we already saw, the antiderivative of x to the 4th dx would be x to the 5th over 5 plus c. The antiderivative of x cubed dx is x to the 4th over 4 plus c. The antiderivative of 3x squared dx is x cubed plus c. If you think about this one, that 3x squared, when you take that antiderivative process, you still have that 3. That squared gets powered up, so it becomes a 3. And you divide by that new exponent, so you divide by the 3, which is why these cancel, and you have x cubed. We'll do another one of these where they don't cancel out and they don't, it's just not some basic situations there. So we'll do antiderivative of 7x to the 5th. Alright? So when I first started doing this, my brain just went, when I was going, it kind of goes crazy because you're like, wait a second, I'm so used to taking the derivative, 35x to the 4th, we got this. Nope. That's not what it is. Alright, so it's going to keep that 7, and then x to the
6.
all over,
Oh, that's weird.
plus,
C.
there we go.
Because you're almost tempted to put the 7 as the new exponent or something.
Right,
like
right,
that.
yep, nope. Antiderivative of 10x to the 8th. See if you can do that on paper. I'll give you 30 seconds while I take attendance. What do you have, Emily?
10x to the 9th over 9 plus c.
10x to the 9th over 9. Is that what y'all have? Pretty good. Okay. So let's think about our trig rules. What is, so maybe over here we should just refresh ourselves, make sure we know all our trig derivatives. What's the derivative of sine? The derivative of cosine? The derivative of tangent? cosecant?
Negative cosecant squared tan, no, cotangent.
So you have cosecant x
Oh, negative cosecant.
and then
Cotangent.
cotangent x. Derivative of secant? Secant x, tangent x, and the derivative of cotangent?
Cotan. No me acuerdo.
Oh, then the
Negative
negative
cosecant
cosecant
squared.
squared.
Tangent.
Alright, so the antiderivative of cosine
Sine. Cos.
Plus
Oh,
C.
no,
is right. If you're not sure, you want to just check it by doing the derivative. What's the derivative of sine x? Cosine x. What's the derivative of c? Constant. 0. So yeah, the derivative of cosine is sine. Now, what's the, it's not the derivative, the antiderivative. What's the antiderivative of sine?
Negative cosine.
Negative cosine.
Oh shoot, that's a tricky.
Think about that for a second. Why is it just cosine?
Because if you take the derivative of cosine, it'd be negative sine.
Right.
So since it's positive sine, you have to.
Yep. Yeah, if you check it by going to the right hand side, negative, the derivative of negative cosine is going to be negative sine. And that's why you have to have that negative there. Oh, it's so mean. We don't have anything so far, any function, such that when we take the derivative of it, we get tangent. In other words, antiderivative of tangent x dx, we don't know.
So it's unknown.
There is something, but it's pretty complicated. And so it's not, in all reality, the only thing that we know how to take the antiderivative of are things of which were the answers when we found the derivative of a previous function. In other words, we can really only take the antiderivative of this stuff on this side. We can only take the antiderivative, we can only go from here to here, from here to here, from here to here, from here to here, from here to here.
Yeah, that's true.
Alright, and tangent is not on that.
Know what the
We don't have a
derivative-
function of which when we take the derivative of, we get tangent. So therefore, if I say, what's the antiderivative of tangent, you're like, I don't know, because I don't know a function of which I could take the derivative of to get there.
So that means we don't know. We wouldn't know like secant or cotangent either.
Yeah, secant, cosecant, cotangent, yeah. None of those that stand alone. The only thing that we really can do is, for instance, I could say, what is the antiderivative of secant squared x dx? And you're like, tangent x
Plus
Plus
C.
C.
plus c.
Or like, I don't know. That would,
What's the antiderivative of negative cosecant x cotangent x? Or what's the antiderivative of secant x tangent x? Or what's the antiderivative of negative cosecant squared? About the best I could possibly do would be try to be tricky and say, what's the antiderivative of positive cosecant x, cotangent x?
yeah, and then we'd have to be like negative sine. I mean negative cosecant.
Yeah, negative cosecant x
Plus C.
dx. Plus c. Okay. Yeah. Okay. So there's antiderivative. This is the antiderivative power rule. We also did the antiderivative of some trig functions. And before we dig into the homework and do some antiderivative of some weird stuff, it would be helpful for us to, I guess one or two other quick terms. This symbol right here, this sort of long S, does have a name. It's the indefinite integral. Actually, this whole thing is the indefinite integral. But anyway, when you see that sign right there, don't we say indefinite integral? And sometimes, I may have even said it this morning, but I will say the integral of blah, 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 dx. So, antiderivative aka the integral. And I will say, what's the integral of da-da-da-da? And just so you know, I'm talking about that phrase right there, that symbol, and we're talking about anti-differentiation. And it's indefinite because it doesn't have a definite answer, or definite number, okay? Because it's blah, 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 plus c, okay? That makes it indefinite. It's not defined. If I knew that it was like plus 5, then you'd be like, okay, no big deal. Okay? But there you go. We will deal a little bit later, I think Monday and Tuesday of next week, with something called the definite integral, and it's awesome. It's super cool. And this is pretty cool too. We're not going to talk a whole lot about slope fields, so I will tell you something that probably means nothing to you real quickly, that I think is just really neat about these functions. And that is, if you think about the family of answers that you possibly get. So let me tell you what I mean for a second. Let's say antiderivative of, we'll just go with that 3x squared dx. As we saw a minute ago, that was 3x cubed over 3 plus c, or simply x cubed plus c. What would the graph of all possible answers look like?
Oh, it would look like
It could look like
an x cubed function, right?
x cubed plus 1, x cubed plus 2, x cubed plus 3, x cubed plus 5, x cubed minus 10, right? You could have all kinds of different things.
Also, the graph would just...
And so you'd have all kinds of really neat graphs. So x cubed plus, I'll just do x cubed. Did I do x squared?
Yeah.
It's cubical. ¿Qué es eso?
X cubed plus 2, x cubed plus 3. Alright, so you get the idea, right?
Yeah.
You know what's really interesting about these? Is they never, like, intersect. I mean, it looks like up here they probably do, but they don't actually. They're all,
They don't?
they don't intersect.
At
No.
infinity.
No. So, anyway, this is the family of curves upon which you get the answer there.
Wow, that's... wouldn't it, since can't the constant be like a decimal too though?
Oh yeah, exactly, yeah.
So wouldn't that mean that they would, like, some of them would be like, so like infinitely close to each other?
says inspire,
Pretty
inspire,
cool.
Oh,
And then-
inspire.
and then
Oh.
it says some in the room. I was
What
like,
is that though? Like, what's inside?
huh?
What's inside of it?
I forgot the
Wait,
difference.
what that is?
Like,
There you go.
I was looking at that
Yeah.
yesterday.
Wow,
Yeah, that's
it's
pretty
going
cool.
up and down.
Because I'm changing C.
So,
C could be any one of those, and as C changes,
but C does cross paths with some of the, like, I mean, I guess when it,
it doesn't. I mean, it crosses when it's the same as one of those.
yeah,
other
I guess
ones.
it crosses.
But the, you know, 2.1, 2.2, 2.3, yeah, those, I mean, you're just zooming in, they still do not intersect.
So I guess no matter how close they get to each other, they're not gonna be the same thing unless they actually have the same constant.
Yeah, it's the same fun, yeah, so, it's pretty neat. What's really neat is if you draw a bunch of slope, we might do slope fields, cause they're just so cool. If you drew a little slopes there and slopes there and slopes there, you get some graphs that look, if you just do all of the tangent lines, like little things like that. See what I'm saying? Okay, so imagine you just drew those little tangent line slivers. You could end up with a graph, or you could end up with something that looks like. Anyway,
So what was your water test?
it ends up looking like a dashed graph, I guess. But that's called a slope field. When you have a whole bunch of little tiny line segments and stuff like that. That tells you some interesting information. And you can use that to represent like electromagnetic fields, things like that. Okay, still plenty of time, and that's good because there's some weird ones on here.
So what would you use that symbol?
We will do odd problems as examples. The evens will be your homework. How's that sound?
Sounds amazing.
Noise.
Makes me have 11 questions.
¿Cuáles son odd y cuáles son even?
I said we're doing evens, right?
So silly.
Hey, we're doing evens, right?
No, we're doing odds.
Are we gonna have to apply stuff like the anti-chain rule and stuff like that?
Oh, that is a great question. Do we have to have like an anti-chain rule? Yes.
Holy
Oh,
cow.
no.
Oh,
Yeah.
I saw that on the notes.
Yes.
It says we have to use chain rule or constant multiple and sum rules.
Mm-hmm. Yeah, there's a whole host of stuff. All right. So the odd ones we'll do together, and then the even ones will be your homework. So immediately right off the bat, it kind of starts you out pretty tricky here. So antiderivative 4x cubed plus 4. So we're going to keep that 4 out there, no problem. And then the x cubed turns into an x to the fourth, and we're going to do this whole thing divided by 4 plus. Now here's a question. Well, not plus c, because I've got this plus 4. What could I have up here such that when I took the derivative of it, I would get 4?
4x.
4x. So anytime you see a constant here in the integrand, that's what this is called, the integrand, then you know that the antiderivative of a constant is a linear term. So that's going to be 4x. And then you've got your plus c. But that 4 over 4 cancels, so we'll just write this as x to the 4th plus 4x plus c.
Do you want us to simplify like that?
Yes. The great thing is, you can check your work. There's no reason why you can't get 100 on this. Because, how can I check to make sure this is correct?
Find the derivative.
Take the derivative of it. 4x cubed, check. Plus 4, check. And then that goes to 0.
Yeah. Way y'all smart.
I think we can handle number 3, right?
Yes.
Let's go to one that looks tricky. How about number 5? Yeah, that
looks tricky.
So I'm gonna keep that -4 right there. What am I gonna do with the exponent of a -3?
Negative.
-2.
Negative, right, turn to a -2, and then divide it.
By negative.
Divide by -2, that's not too bad. Minus 9x to the
Third,
Negative.
-3 all over.
-3.
And we just do a little bit of simplification. -4 over -2 would be a +2. -2. A negative and negative turns into positive. 3 and then 9 over 3 is 3. -3 plus c. My answer key might shove those negative exponents down into the denominator.
Can become positive.
So yeah, just and make them positive. So if you want to make your life easier when it comes to grading, anytime you have negative exponents, just put them like that. Chloe, pick another odd problem for us.
Number 9.
Okay. Well, that's just the reverse process of what I just said a second ago. Just tell me, how would you rewrite this problem, and then we'll move on.
You rewrite it to x to the -2. So never mind, not number 9.
Minus 8x -3
Yeah.
minus 20x to the -5. So it's literally just like that other problem. And Rosa thought this was going to be a long one.
I take it back. 13 looks pretty difficult.
All right, let's do 13.
Oh.
Oh, then they have like
Why is there all like that? Maybe it's just like.
What about 11?
Yeah, that
Both
was.
of those look hard.
Okay, let's do 11 first. All right, so
Oh my god.
just apply the process here, Chloe. I'm going to keep that 14 and that 3. I'm going to keep those as is, right? So, what's the process here?
Add one.
Add 1 to 4/3.
That would be to the 7/3.
What magic is this? Can y'all convert 1 to 3 over 3 in your head? Sure, if not, you can remember that 3 over 3, you have to have a common denominator, right? Okay, 4 plus 3, yeah, alright, so there we go. But wait, we then have to take this whole thing and divide it by
the new exponent.
divided by 7/3. Or you could go beast mode and realize that anytime you have something divided by a fraction, it's the same thing as multiplying by the reciprocal.
Holy cow.
Can you remember to do that right away, or yeah, you got some room there in the paper? Plus, we'll keep the 40, we'll keep the 5. We have x to the
8 over 5
8 over 5
times 8 over 5.
times what?
8 over 5?
Not times 8 over
Oh,
5.
no, 5 over 8.
Times 5 over 8. Because we were dividing by 8 over 5, which would be my same thing as
Plus
multiplying
C.
by 5 over 8.
Okay.
Almost snuck away from us, thank you. Saving us. Let's see. Then it's just a matter of doing some simplification. So those 3's cancel, that 14 to 7 reduced to a 2x to the 7/3 plus 5's cancel, the 40 over 8 reduces to a 5. So 5x to the 8/5 plus c. Now is a good time for us to remember, what does it mean for an exponent to have a fraction, or sorry, a variable to have a fractional exponent. What does that mean?
Oh, it means the square, like the whatever, not the square root, but like the root, the whatever, like the denominator is. You take that's the what is that called? The number that goes inside the
Yeah, it's the root.
The
Yeah,
root.
The
Is
root,
the-
the nth root.
and yeah,
So, for instance, x to the 1/2 corresponds to
square root.
the square root of x. X to the 1/3 corresponds to the
Cube root.
cube root of x. So, x to the 5/2,
Square
you
root
can
of
think
x
that
to the
as
fifth.
x to the 5th to the 1/2. Which, because, 5, and we have power of a power, same thing as multiplying, so you can have that. So this would be the square root of x to the 5th. If you had x to the 2/3, that would be the same thing as x squared to the 1/3. So that's the cube root of x squared. So far, so good? So x to the m over n means
The nth root of x to the m.
so I could have rewritten this as 2x or 2 times the cube root of x to the 7th. And that's going to help us out with the next problem. Because we're going to rewrite this as 5/3 x to the
3 no
2 over 3. Yep. The exponent here is the numerator, and then the root, the nth root is the denominator. Plus 28 over 5 times x to the 2 over 5 plus 5 over 2 times x to the, there's a 1 right there, so 1 over 4. And we just did a problem like that. Didn't we?
Yep.
Okay, so this is not so scary, just a little bit of algebra. You show that to your algebra students, friends, though. You'll be like, hey, check out this. And they'll be like, what in the world? That doesn't make any sense. What's that symbol? You'd be like,
calculus.
it's the antiderivative.
Still gets it wrong and fails the test and gets a 23.
15 looks pretty straightforward. 17, I'm just trying to be tricky on you there. I think the rest of them are,
Pretty reasonable.
yeah.
What does that R mean?
It's just an X.
It's just a variable. It doesn't really matter if I put an X or an R or an S.
It's radius.
But I wanted you to, you need to be comfortable with having other variables of integration. Sometimes they're called a dummy variable. A dummy variable, because, not because they're unintelligent, or because they get,
Just a decoy.
because there's like a decoy. Yes.
Could we work out a problem with a variable, with a number in front of one of the trig functions?
So why don't I just modify 19 to have a 5 in front?
Okay.
Noise.
So you just keep 5, and then just ask yourself, what is the antiderivative of sine? Close. No, it's cosine S, and then
Plus.
plus C. Now let's check our work, okay? What's the derivative of 5 cosine S?
5 sin S.
Sine S plus.
Well, no, not plus C, the plus C.
Oh yeah, that's true.
But actually, that's not correct, because the derivative of cosine is
Oh.
Negative cosine.
negative sine.
Negative
So this
sine
needs to
of
be negative cosine.
Aha.
So yeah, that multiplier out there is literally just a multiplier.
You're right.
So
You
just
could.
carry it on there. Okay? Looks like tomorrow you need to have notes on 5-1. Tomorrow we'll officially begin, so anyway, it's kind of like a preview for it, but the second half of calculus. Calculus is everything is derivatives and antiderivatives, slopes and integrals, slopes and the area under a curve. It's all about slope and area. That's all it really boils down to. So tomorrow, we are going to start the process, Hector, you're going to love this, of being able to figure out what is
Shading.
that area.
That's like what they invented calculus for.
That's one of the reasons,
One of the
yeah.
reasons.
And you're like, I can't do that. It's got like curves in it and stuff like that. You can. How would you find the area of something that's kind of got curves on it?
Derivative.
Whole bunch of derivatives.
Screw about that. I'm throwing that out there.
Slope
No,
of a tangent.
that was for finding slope. No, not slope. We're finding area now. Area is a different phenomenon other than slope. So that's what we're going to be doing. Find the area. And we're going to use pre-calculus just to get started on it. We're going to do some approximations.
So there's a pre-calculus way of doing that.
Mm-hmm. Yep, that's what we're going to be doing tomorrow. Approximations. All right, so today we're talking about antiderivative.